Okay, so let's continue the flow of analysis. The pipeline we have seen so far start from files with features about candidates and about job offers, and then through matching function build this fitness matrix, which contains for each required feature by a job offer and each candidate to that job offer, how much the features of the candidate satisfy, match the required features. This can be 0, 1, or it can be a fraction. The fraction language is known, required language is known. This fitness matrix, together with the historical score of the candidate for that job offer, is given in input to train a machine learning model, which learn to rank based on the score given the observed fitness matrix features. Once we have new data, we simulated the new data with the test data. We can ask the machine learning model to make scores given the features, the fitness features. These scores are used to rank candidate from the highest to the lowest score. Today, and so we have seen yesterday the preprocessing part, how to build the fitness matrix, the ranking part, how to train and test the ranking model, and the fairness part, which is one special type of ensuring fairness on the by preprocessing the fitness matrix and removing possible correlation between a protected attribute we consider gender and the distribution of the data in the fitness matrix. Okay, so today we'll start looking at explaining the predictions. And so we will see a workflow which, given an instance, a candidate to be scored, give an explanation of the score received. Let's see what is the plan for today. So we will have, like yesterday, a short presentation of the book, or the notebook for explainability, and then some practice in the style of yesterday. So you have to modify parameters and see what happens. Then we'll have a short break. After the break, we move in a plenary session. So in presence, we go on the main room, and it will be presented a case study inspired by the same workflow. Since programmers and non-programmers have seen different tools, we have seen Python non-programmers K9. Don't worry, because actually the logical flow of Python and K9 is exactly the same. It's the coding which is different. However, since non-programmers do not know Python, the case study will be presented using K9, but you will recognize in K9 the flow of Python very, very easily. After the coffee break, there will be another practice, this group work, in which programmers and non-programmers mix. So you will stay in the main room, mix with non-programmers. People online, both programmers and non-programmers, will mix in breakout rooms and discuss the case study. There is, after the discussion, an individual questionnaire to be filled. And then we continue in plenary session up to the end. Okay? So after this break, you will move in the other room and stay for the rest of the morning. Okay, let's go back to the first topic, explainability. How can we explain the score assigned to a candidate for a job offer? There are many tools and explanation actually can be given with several respects. We will see one explanation method which is based on feature contribution. It means to assign an importance to every feature given in input to the ranking model in order to understand which feature contribute the most to the score predicted. Let me recall this notion of Shapley values, but we will start with the output of the system, which are these breakdown plots. So assume that you are given, the system is given in input just one row with the features of a candidate, and the total score predicted, this fx, as a certain value, which is this black line here. Okay. Now we could think that this predicted score is consists of a sum of weights for each of the predictive features. So we linearize the predicted score using weights for every feature. For instance, years of experience in this example as a weight which is given by this blue bar. So it is a weight which increase the prediction. If we add only years of experience as a feature, we would end up from 0 up to 0.4. If we add also education level, the score would increase, the education level of that person. We would increase. The GPA of that person instead is shown in red because would decrease the score. Okay, so by considering adding more and more features of the specific person, we arrive at the final predicted score. Okay, so this is the contribution of the specific features for the instance to be predicted, but this order in which we consider specific feature is arbitrary. Why we should start from year of experience or and then add education level, GPA, and so on. So breakdown plots are arbitrary. The Shapley value just consider all possible orderings of feature, of adding one feature, and average over this ordering. And the meaning of the contribution is the marginal the marginal score that on average that feature contribute to. Okay. So this will be the output of the explanation, and the meaning with reading is for the Shapley value is the average contribution to the score for each feature value we are considering. This is the theoretical Shapley value. You may easily figure out that all enumerating all possible combination is very expensive because there is a factorial number of such permutations, no? So there are some approximation. SHAP is a library which implement this approximation. Okay, let's go to our notebook. So notebook 04, explanation. The first part in the notebook is to build the model. We do not repeat all the steps, but we just call the notebook ranking model, or the notebook fair ranking model if we want to explain prediction of the model with the fair preprocessing. So this can be nicely done in Jupyter notebooks with the directive run, which takes the name of a notebook and run all the notebook. So in the output, we get all the output of the ranking model. Okay. Now, let's explain some specific predictions. We will use SHAP library and assume that we want to explain the score assigned to candidate ID 24,000, which is a candidate to the job offer number 160. Okay, so this is the row for which we want to explain the prediction. And so X is just of the data set for the job offer 160, the one of the row of this data set. So in particular, this instance has 0 fitness contract, so did not match the required contract, match the gender, but every candidate matched the gender because recall we fixed the requirement for gender to any. Match the nationality, match the education, match the experience, does not match the age, does not match the required languages, does not match the required competencies, does not match the required knowledge. The gender of this candidate is female. The true score, recall these are historical data, is 0.28, and it was ranked 8 in the past, in the historical data. The predicted score, we call it lambda, is minus 5.4. This is lambda is the relevance predicted by the model, which is not necessary between 0 and 1 like the historical score. And using this lambda, predicted lambda, the predicted rank is 11. 11 actually means, since we fixed the top K to 10, means out of 10. And it is a protected attribute, a protected person, because female map to protected. Okay? Now, just to double check the predicted lambda, if we ask the ranker to make a prediction over that instance, passing the predicted columns and taking the result, we get an error. Why? We should not get an error. Maybe I did not run the initial one. Okay. Okay. So this is just to double check that the lambda is actually the one predicted. Now, we want to explain this instance. So we assign to explicand data. Let me zoom a little bit. To explicand data, the columns, the predictive columns from that instance. In order to generate, let me go back to the slide. In order to generate, to calculate the average contribution, the average marginal contribution, the Shapley value required to do an expectation. An expectation over what? Over other person which apply to the same job offer or to similar job offer. So basically, doing expectation means take the instance to explain and replace some of its attribute with attribute of other persons and see what happens. So in the code, we need to define a collection of persons with the similar or applying to the similar job offers. And actually, the reference data in this case is exactly all the applicants to job offer 160. Okay. So this is needed because we need to do the average contribution of each feature over a reference population. So we can create now the explainer by using SHAP kernel explainer. This is one of the class in SHAP which implement the approximate calculation of Shapley value. It requires the prediction function, so the predict of the ranker, and the reference data. What this explainer return? It return the expected value, which is the average score over the reference population. So for the job offer 160, on average, the applicants received a prediction of minus 2.78. Okay, and if we look at the slide, this is this V0 is what is independent from the features. So if we have no feature, we can assign the average prediction to an instance which has no feature. Then we can ask to the explainer to make instead to assign contribution to the explicand data, which let me recall are the predictive features of the person we want to explain. In this explanation object, this explanation object can be cast to a data frame in which we have the Shapley values of the object, and we can give a name to this Shapley value. So let's visualize better. Fitness contract contributes minus 1.4, fitness nationality 0, fitness education 0.39, and so on and so forth. So these are the values, the SHAP values, the approximated Shapley value assigned to each feature for the specific applicant we have considered. So with reference to the slides, the numbers in the sum here. If we sum all these numbers plus the expected, we would get the total sum will be the predicted value. So in general, the lambda assigned to the instance 24,000 is given by the mean value of over the reference population plus the sum of all contributions, all Shapley value for each of the feature. So if we do this double check, we see that the sum of the Shapley values plus the expected value is minus 5.47, which is exactly the predicted lambda. Okay, so this shows in this example shows that the predicted lambda has been linearized into the contribution of each feature. This linearization means that we can look at the contribution of each feature as a direct value independent of the other because it is averaged over the others. We can now visualize the breakdown plot. It is called a waterfall plot. What is the difference with the breakdown? In the breakdown, we have an arbitrary order. In the waterfall, the order is given, is independent, the value of the Shapley, or the contribution, the Shapley value is independent of the order because it is prefix average over all possible order. So typically the visualization is from the attribute with the highest Shapley value to the lowest, highest in absolute value. So not having, for instance, in this example, not matching the contract is given the highest absolute Shapley value, minus 1.41. Okay, so this feature contribute the most, and its contribution is toward lowering the predicted score. Then the fitness age and the fitness competencies. Notice all these fitness are 0. This means lack of agreement between the required contract and the candidate willing to do that contract. Or for the age, the age candidate was not in the boundary minimum maximum age required in the job offer. Instead, the matching, the feature which matched contribute positively to the score. Unfortunately, their contribution does not compensate the negative contribution of the other features. Okay? So what we can see is that the sum of all these contribution is the predicted score, minus 5.47, okay? And the average prediction for the population is minus 2.78. So the score predicted for this candidate is much lower than the average on the reference population. So by looking at this waterfall plot, we can understand for the specific candidate what contribute, and so what could be changed also, no? So, for instance, here we see fitness contract contribute to lower the score. If the candidate in the next application is guided to be more willing to adhere to the required contract, that would be a suggestion for improving future scores. So the purpose of explanation is also to understand why, but also to guide how to improve the score. A variant of the visualization is this force plot, in which we have the same contribution, but shown on a single line with the like forces that push down or up the predicted score. Okay, so we have a fitness contract which push down and experience which push up, but in the end the prediction is minus 547. I like much better the waterfall plot, is more clear to understand. Yes. Exactly. The starting point here, if you read the bottom up, yeah. If we start looking bottom up, without any predictive feature, the best we can predict is the average score of the population. So this is the starting point. Then by adding one feature at a time, we correct, we increase or decrease the score based on the contribution of this feature up to all the features. After fitness contract, we have all the features of this candidate, and the corrected, the summed total is the predicted score. Okay, if you read top down, you start from the most important feature up and remove that feature. By removing that feature, you go towards the average. One last point is, okay, disregard a single candidate, candidate number 24,000. This is a local explanation in the sense that we fix a single prediction and want to understand why that prediction. Sometimes it is useful to understand over a multitude of candidates what are in general the feature more important. Okay, so this is the last cell. it is shown in this decision plot. This decision plot takes the average value and the Shapley value, not for a single instance, but in this case for 100 instances sampled from the test set. Okay, and plot the contribution, the Shapley value contribution over these 100 features. What can we see from this? We can see that competence and contract, typically the presence of competence and contract typically impact on predicted importance, on predicted score, much more than the feature in the bottom. Okay, so for, like in the previous plot, if we had no feature, we have the average value. By adding gender, languages, nationality, we do not change a lot. So the contribution of gender, languages, and nationality to the score predicted by the model on average over this 100 sample is negligible. So they are not important, do not affect the predicted score. Instead, the top, the feature listed in the top, they impact because they change in one sense or the other, match the score. Okay, so this is a way to look at a global explanation. What are on globally the contribution of the feature in the model? This can be useful for several purposes. For instance, if we have to do feature selection, we have a lot of features we want to reduce. We could say, okay, gender, languages, nationality, they are not impactful, so we can save computing these features. The other way is, okay, we want to understand, based on the historical data, what are the features that the model infer as more relevant, more correlated to the historical score. One final point, look at fitness gender. This is how much the gender required by the job offer match the gender of the candidate. Its contribution is 0. This is natural. Why? Because in the job offers, all the job offers have any as a requirement. So actually, all the applicants match this, so there is no information. Does it mean that the model is fair? The fact that gender does not contribute? Okay, the answer in the room is we don't know. This is not the direct. This is only the direct contribution. Okay, but there could be some other attribute correlated with gender, which takes importance, not attributed to gender. This is called indirect discrimination. So the model learn to discriminate not directly on the gender, this is not the case, but on proxy attribute correlated with the gender. And we will see later on that this is the case. But by the way, from the result of yesterday, we know that there is unfairness in the model. This unfairness is not explicit in the gender attribute or in the fitness gender, so it must be indirectly learn from correlated. And a typical example in the history is in the US redlining. Redlining is in segregated cities, the fact that neighborhoods are inhabited by whites, black, and Hispanics. So banks discriminated on loans based on the neighborhood or residence. Okay, so they were not explicitly using race, but a proxy attribute which with high probability identified certain social groups. Okay, so if you are asked, but my model does not use gender, does the model how could the model discriminate if it does not use gender? Like in this case, it's not using because importance means it's not using. And the answer is it could discriminate through proxy correlated attributes. Okay, now we split into breakout rooms, and we'll do this exercise in the style of yesterday. So basically, one of the person share the screen and try and modify the parameters or look at another instance instead of 24,000 in order to understand if the contribution change and how. Okay, let's just summarize before a short break. We have seen this method of explaining the predicted score. This is not the only one. There is a large collection of methods. This is one of the most well-known, yet it is not a method specialized for ranking because it explains scores, whatever the score is used. Could be a credit worthiness score. In ranking, the score is used to rank. So if you have done some variants of the notebook, you may have noticed that fitness contract is important when we have protected applicants. If let me change just to show a candidate, this other one, 24003. This is a male one, so an unprotected. And let's see what change in the predicted score is -2 is better than the previous one. Let's have a look at the plot in this case. So we can see that in this case, fitness contract plays in favor of increasing the score. Okay. So just take this in mind for future when we will disclose how the synthetic data is made unfair. Basically, just to spoil a little bit, we have correlated the contract with the gender, like male prefer in presence and not male prefer remote contract. And so basically we injected injected a strong correlation in the data set. So actually fitness contract include the information about the gender. So the gender is not relevant explicitly, but indirectly it is. Okay, what happens now? We take a 10 minutes break. Then we will move in a plenary session, which means we will not use anymore for today. We will not use this call, but there is another call planned, plenary session. Please disconnect from this call and connect to the plenary session. In the plenary session, there will be first the presentation of the case study, then a coffee break, and then some group work. People in presence will do the group work in the main room. People online will do the group work in the plenary call, mixing programmers and not programmers.
So can you hear me?
Yes.
Okay.
Yes.
Now you are asked to work all together. And because we would like to replicate the case studies we faced in the case studies part, the algorithmic discrimination in candidate selection. If you don't remember this case study, I will tell you how it works. There is a candidate who is trying to, he is a black candidate who is trying to apply for a job offer. And his application is always rejected. Okay, then what does it happen? He wants to know why his application is rejected. Okay. And what we want that you learn is to understand the difference between a fair score and an unfair score. I remember you that the ranking is performed with the list of candidates that are applying for this position, okay? And everything is based and compared to the score, which is our ground truth. Okay, without ground truth, we are not able to perform any analysis. Okay, we have to start from this ground truth. Okay, then what is our aim? Our aim is to compare the normalized discount cumulative gain, okay, and the statistical disparity metrics, okay, between the two score. Our historical data. So I will teach you how the score is computed, is created, okay? And we will compare the score fair and unfair, and then we will observe the results. At the end of this explanation, we will have the break, and after the break, you will be requested to work in pairs or in groups, okay? And to answer, to do an exercise on book club, okay? And you should arrive to create the without looking at the screen, of course, in order to see if you understood what we explained to perform the analysis all together and to create the pipeline of the actions that are requested to arrive to the final results without looking at the screen, but only I will show you the exercise later, don't worry. But this is very important to understand if you understood what we explained, okay? It is a really simple exercise. Now I will try to explain the case studies, the case study. If I find it, yes. Okay, here we are in the case studies. So the workflow number 5 for the programmers. I don't know if you know KNIME. KNIME is a visual data analytics platform, and which makes use of nodes to perform the analysis. Every node has a particular function behind, and so let me show you for the programmers, just a moment. For the programmers, you can select the list of nodes from the left and simply drag and drop there the nodes in order to apply a function to the data set. To read the data set, to read the data set, you simply have, so it's clear, you simply have to insert the path and everything will appear here. The execution of each node creates the results, and you will see the results here. Okay, you will see the results as soon as your mouse is over the nodes. Okay, so here we read the fitness metrics, here we read the score, and you see that the table changes. Here we join, so the word is the same, like a join, while in internal join is performed between the fitness metrics and the score. Okay, so for programmers, we have a pipeline and we have a number of annotations, so the colored square that tells us what this node is computing. Okay, so here we read the data set, here we sort the values by QID, here we split the train set and the test set, so it's the split train test, and here we have our algorithm, the learner, so everything is behind. So this node has been implemented to perform the lambda mart learner, and the result is the model. Okay, and here we have the predictor of the lambda mart. Okay, so this was for programmers. Now, how the score is created, so our ground truth. First of all, I have to remember that the score is the historical data of a company. So we have a company and all the historical data, so our ground truth. The score can be fair or unfair. Why? Because for every company, we have a feature importance. So what is a feature importance? The importance that we assign to every feature. So for my company, for this job offer, for me, in a scale from 1 to 10, the education has an importance of 8. Since I'm a fair company, the gender has an importance of 0. What does it mean, an importance of this 0? This means that for every candidate, since I can be male or female, if you multiply this feature importance for 0, 1 for 0, and 0 for 0, the result is always 0. So this is not important because every candidate will have the same, always the same result. Okay, so the importance is 0. For instance, my level of education is 2 and the feature importance is 8. 2 multiplied by 8 is 16. If my level of education is 4 and the importance is 8, 4 multiplied by 8 is 33. So the double of is 16. Do you understand what the feature importance is? This is the weight of my final score for every feature. So if the feature importance is 0, everyone will be considered at the same. level. Nationality 0, because I'm a fair company. So if you are Chinese, African, European, for me is the same. The age, I was explaining that before, there can be a difference. So there can be jobs that requires a minimum level of age. So I can be 16, for instance, or for instance, in America, you can be 16, but not in Europe. Okay, so there can be a difference. The contract for me is not important, because if you work remotely, if you work in presence or an hybrid, for me is the same. Okay, experience the same. Languages, competencies, for me competencies are very, very, very important. And knowledge 8. And I'm considered a fair company. Pay attention to the fact that gender and contract are bold. Okay, so we will came back later to this aspect. Okay, unfair. Are there any questions up to now? Is everything clear? Okay, then I'm at a society and I'm not fair. I'm unfair. The education is 8, the gender is 0. Oh, but we said that if gender is 0, this means that this is not important. Okay, correct? But because everyone will have the same results. Is it correct? Yes. So we have 0, and nationality is always 0. So I'm a fair company. Yes or no? Yeah, but pay attention, contract is 8. This is called redlining. What does it mean? This means that we can have a gender, so a sensitive attribute, which is 0. So every candidate will be considered in the same way, but the gender is correlated to another attribute. And to make you understand, we correlated our data to the contract. What does it mean? This means that the majority of female applicants have, or in their CV, a remote contract, whereas male applicants have in presence. The system will learn that all female, even though the gender is not important, we learn that all female applicants have remote, and all male or female or not, and no, not binary, so not male, and all male will have an in presence contract. This is subtle. So this is not clear because the gender, the feature importance for the gender is 0, but we have, since this feature is correlated to another feature, this correlation will be learned by the system. And you will see how this changes the final results. So look at this. Sorry. Look at this. Okay. We have a fair company here. We apply our algorithm, our ranking algorithm up to the end. And we calculate, as before, the statistical parity. We learned to calculate it yesterday. What we have at the end, so I go up to the end, and here we have a bar chart, and we can see that not male are more than, that male 0 are more than not male. Okay? In our final results, we calculate the statistical disparity, and this level should be very, very, very small in order to have a balance. Yes. This is dataset FAIR. Okay, sorry. I repeat it. Yeah, because I repeat. So here we should have fitness matrix 1. Okay, and then you can play with that. And dataset score 1 FAIR. I will check. Give me 1 second. Okay. Okay. And at the end, okay, so this is fitness matrix 1 and score 1 FAIR. Okay. At the end, what is our statistical disparity, Andreas?
Yeah, just one question. Is there the same number of male applicants than female and non-binary?
No. So we will see it here. So here we have, I didn't focus on this analysis because you performed it yesterday. So, but I will show you. So like to review some aspects. So here we selected the top K applicants. Okay. Top K for us is 10. So out of all the applicants for this job offer, we want to know only the top K, so the 10th up to the 10th position, okay? And for male, we have 215 selected out of all the applicants for this job offer, and not male, 185, okay?
Yeah, but my question was right at the very beginning, before any selection has been done.
Okay.
Is there a parity between male and female and non-binary? Because if I have like 80% male applicants and just 20% female, it's clear that the outcome would be then skewed towards it.
Okay, so we will see in these other. So these are the numbers of applicants. These are the total number of applicants, and you can see as soon as I show you the results that we have less male than females. Okay, females are not binary. So we have 472 male applicants and more than 2,000 of not male applicants, so female and non-binary. Okay.
Mm-hmm.
How many of them are selected? As soon as you see here, you can see that there are more male than female selected. Okay. Despite the number is completely the opposite. If we go up to the end, we can see that the statistical disparity, however, is little. Okay, what is the statistical disparity? We see it before, is the difference between the two proportions of not male selected in the top K and male selected in the top K. So here we have a small, this value should be small. And because our data set, we say that our score is fair. Look at that. So here we have an unfair feature importance to calculate the score, but this is not so clear from the beginning. Why? Because the gender is 0, and so we can say to whom? To so for instance, for to systems that are, or companies that are verifying if your feature importance is fair, if your score is fair, if your company is fair, and you show that you consider the gender as 0. So you can state that your company is fair. So the question is your company really fair? Or there can be a correlation between your gender and another feature in your feature importance. If we see the results, so here we use the same data set, fitness matrix 1, and the unfair score, which is computed with this feature importance. So the gender is always 0, so 0. So I can assume that I'm a fair company. However, this red lining, so something that is subtle, that is under the truth, tells me that the contract is 8. This is the unique values that changed, okay? Because here we had 0 and the rest is completely the same. We didn't move anything. We didn't change anything. Okay, here, the only aspect that changed in this unfair score is the contract. If we go up to the end, okay, so here, the number, look at that, the number of male applicants selected in the top K is almost 400. And the number, we didn't change anything in the workflow, in the pipeline. Any parameters you can really check for non-programmers, you can check all the parameters are the same. We simply change the correlation with the contract. Okay, and here you can see how this number changes. So before I go up, this number was 215 and almost the same. So there can be a difference. It depends on the curricula that have been submitted. Okay, so this can be a different because of the type of curriculum, but the same curricula, the same algorithm parameters, they are all the same. What does it change? The score, okay? And the score of gender, the feature importance of the gender has been correlated to the contract. For you, oh, the contract is not important. For me, if I work remotely, if I work at home, it's the same. But to make you understand, we correlated the contract to the gender. You don't see it because the gender is 0. So you can assume that you are a fair company. If you look at the results, here you have, with the same curricula, the same algorithm parameters, the same, everything is the same. You have almost 400 male people that have been selected. The number of applicants is always the same. So look at that. Applicants, here, applicants, here, the same, selected in top K, 200, and here, 400. At the end, what do you have? A statistical disparity, completely different. Okay? And this is very, very, very subtle. This is slightly different in the contract, but the system learns that there is a correlation between the gender and the selected contract in the CV. And this can be considered a very discriminating result, even though as a company, I can assume that I don't consider the gender, because the gender for me is 0. Okay, is that clear? Is that clear? So this is really an example of how the score can discriminate candidates, even though the appearance is completely different. We say the gender isn't important for me. So any of you can be enrolled, but since there is a correlation between the gender and any other feature, we use the contract to make you understand, but it can be with other features that are requested in my job offer from my company. You can see in this example how the final ranking can be discriminating, how the final ranking can be applied with an appearance of fair company. Are there any questions? Yes, Andreas. Sorry, I wasn't aware. Yes, Andreas?
I think Shaz was the first one.
Yeah.
Who had a question.
Okay. So,
Yeah, shall I go first? So my question really, Daniela,
yes.
a very non-programming question, but you've used the algorithm Lambda Mart, so I saw
Yeah.
that was kind of the funnel, but have you tested this using a different algorithm to see if you got the same result?
This is one of the algorithms that we implemented, but this is one of the most used in the ranking. We, in our project, not for this course, but in our project, we are testing other ranking algorithms, and the results are always the same, because there is a correlation. Yes, the correlation between, in this data set, between the gender and the contract. And many companies can play on that. Okay, so this is to make you aware of an appearance of anti-discrimination behavior. So a fair feature importance can in fact hide a discriminating feature. So this is really clear. Okay, so the only thing we change in everything, is the feature, is the weight, the feature importance, the weight of the contract. And it wasn't clear from the gender. So for me, the gender is not important. I can assume that I'm a fair company. So I can say, oh, I would like to hire all genders. Okay, but it's not true, because the gender is correlated to, can be correlated to another feature, which is not so clear, because it's not a sensitive attribute. The gender is sensitive, but the gender is 0. Okay, the gender is 0, like in the fair. No questions. Julie, are you inside? Okay, because I always receive this message. Are there any questions? No questions? No questions? No questions? Okay, break. We can, Andreas, yes.
Just to check whether I understood this. I assume that then in the raw data, there must have been the majority of the female applicants actually wanted to work remote, right?
Exactly.
And that's why there is this correlation. So another example, the classical example would be part-time or full-time.
Perfect.
The same, right?
Exactly.
Yeah.
Is that exactly?
Daniela, show the slide, the last slide.
Yeah. Yes. Okay, here. Do you want to explain it, or Salvatore? Yeah, go ahead. So
yeah, you can see from this slide that we injected this correlation in the unfair data. Majority of female have a contract 0, and majority of non-binary have a contract 0. Instead, the majority of male have a contract 1. And the example you made about part-time is another typically correlated feature with gender. So in our synthetic data, we injected this, but in reality, it's much even more complicated.
And my question is, there might be many other features that are correlated to some extent, right? And that makes it then, in the end, very difficult, because it could be job experience, since women probably are more often the child carers and don't have so many years of service. So that might be a correlation too, or whatever other feature there is. So in the end, with this program, you can find out correlations, right? I understand, between protected features with protected features probably, but in the end, the solution might be difficult in some.
Yeah,
some cases,
the FAIR pre-processing algorithm was intended exactly to find out and decorrelate all or the most evident correlations. So the FAIR algorithms are intended exactly to discover these a priori unknown correlation and they correlate the data. Okay. And it's not simple. You are right.
Mm. Thanks.
That's why we are working in this direction. Yeah. For anti-discrimination in hiring, because a number of systems can hide this aspect that are apparently fair, but because their score it's apparently fair, but it's not true. Okay, that's why we are all here. Are there any questions? Other questions? No? Yes, Ivor.
Yeah, thank you. Yeah. Very nice funding. Oh, yeah. Go ahead.
My question. Mm-hmm. Yeah, my question is how has this been taken on board by industry? How has the recruitment industry and big players involved in big software players like Salesforce, how have they taken this on board? Are they keen on this type of work, or?
I didn't. Yeah. Sorry, but I didn't understand the question, Salvatore.
Yes, the question was whether the industry from the sector has been involved in this research. There are two aspects. From the research aspect, novel proposal of fair models are tested against available test datasets. And this dataset may be in collaboration with players of the sector. The second aspect, but this is for the moment minimal collaboration. The main point is since the starting of the AI Act, the screening is considered a high risk application of AI. So company will be forced to do this kind of analysis. So the game starts now, actually.
Thank you.
I suppose there was another question. No? Okay. Yes. Yes.
Yeah. I think I got a maybe similar question about the data sites, because I suppose that for companies, maybe they they are not willing to share the data, right, with you because you want to, you know, pick up some kind of discrimination bias in their data sites. So my question is, how did you get the data sites? Collaborated with them or in some ways?
So concerning the CVs, we have our generator for synthetic CVs, but if you look in the FINDHR site here, we have a call for action: donate your CV, and we collected a huge number of CVs because the FINDHR project is not only this training course, but we are as you can see here, we are a number of university and companies that are working in this direction. Okay, and so we are collecting CVs in order to analyze the results of our algorithms. So this can be a starting point. And in order to train at the very beginning our algorithms, we use this synthetic data set, not the only one that you are using for the course, a more complex one. So the course was really, the synthetic data set we used for the course was really simple in order to make you understand the main points of the analysis of this pipeline. But we have a number of CVs and job offers that we are analyzing in real scenarios. And this is only a small part that you are looking for, that you are participating in.
Thank you.
You're welcome.